It is a well-known distribution, so it's going to be quite brief. And next week, hopefully, we shall look at the log normal, which sometimes we tend to use in econometric analysis, which we will do next semester. But today we want to look at normal distributions. Okay. It's very, very precise and concise lecture. And like I indicated, is the most widely used model for random variables. Random variables that have continuous distribution. This is the most. Can you tell me which other random variables with continuous distribution, apart from this? Who can give me another? Who can give me another? I think this guy is on your page, isn't he? The other Albert Kofi. Is he not on your page?
Yes, Doctor. Thank you. Yes.
Albert, can you call your friend to join us?
Yes, Doc.
Okay, so I was asking to give me one of the other distributions that are continuous.
Doc, hypergeometric distribution.
What else?
Doc,
Something. What?
The Poisson distribution.
Will you agree with that, Emily?
No, Doc. Poisson is not continuous, it's discrete.
All right, so these distributions of random, they are the first examples you will face when it comes to probability density functions, because they cannot be integrated in the closed form, and you see that pretty soon. So we can't use cumulative distribution functions for them using the standard algebraic techniques. So the cumulative approach of calculating, like we did with the others, gamma and hypergeometric. So you see that the way we subtract them, we are not using cumulative for them. So let's try to understand the random distribution, the normal distribution. So a particular random variable x is said to be normally distributed with a mean mu and a variance sigma square. Now, if you take away the square, what is a sigma? If you take away the square, what is a sigma?
That's the standard deviation.
So standard deviation.
Okay. So that is a standard deviation. So we write it as x is normally distributed with a mean of mu and a variance of sigma squared. Now, that means that we need to know the probability density function for x, that random variable. The probability density function is given by this information that you are seeing here. And this has things like pi, it has things like the variance, it has the exponentiation, it has the mean, and of course, from the variance, you can find the standard deviation. That is a probability density function for a normally distributed random variable. It has some features. As you all know, if you try to draw it, it's like a bell-shaped curve, symmetric around the mean, which means that the center is the mean. Now, the mean is one of the random variables. So if everything on the x-axis here is x, the mean is one of the x, or the average of the x. So the mean is actually representing the center of that, the distributed random variable. The distributed random variable. The other thing you will notice is that it doesn't have bimodality or multimodality. It is unimodal, one peak. It can be from negative infinity to positive infinity. So the values of the x can be from negative to positive infinity. It is also completely determined by two parameters. Once you know the mean and the variance or the standard deviation, you are good to go. So why do we need normal distributions? Well, the reason is that they naturally come from the central limit theorem, which says that as you increase the observations, you now get closer to the true value. As you increase the observations, you are inching towards achieving the true value. Many physical, biological, economic phenomena are approximately normally distributed. Can you give me examples of certain things that are approximately normally distributed? Mention some of them for me, Jerry. Albert Kofi. Emily.
Doc, marks in a class, like exams marks in a class.
Good. What else? Apart from exams in the class. What else do we have that is normally distributed?
Age of a group of individuals.
Ages of a group of individuals. So where that group might be students in a class or another kind of things.
Yes.
What else?
Doc, the height of students in a class.
Height of students in a class. So all of these things are normally distributed. So we have so many things in life. For example, the moment a baby is born, the weight of the baby. The weight of the baby is normally distributed. Generally, approximate weight. Some will be big, some will be small, but the average weight of the baby is normal. The other reason why we use normal distribution is because it's mathematically tractable. Okay. The closed forms for many transformations. So you can do binomial approximation to normal, gamma approximation to normal. Okay. Weibull approximation. You can convert certain things and approximate them towards the gamma distribution, towards a normal distribution. So even if you have something that is binomial, you can approximate the binomial to normal. You can approximate it. Okay. Now, let's look at the definition of the standard normal distribution. So we give the normal distribution, but the standard, because certain things are normally distributed, as we have said, but then they don't have the same scale. For example, the weight of a person is measured in kilograms, but the height can be measured in inches. You can have income or salaries of a group of people, which is normally distributed, but salaries are measured in currency. And you can have gallons of water that the average household use, and it might be similar, normally distributed, but that is measured in gallons. So the unit of measurement is not common. It's not the same. You got to commonalize it, standardize it. And this standard normal distribution formula can help you to standardize any number into a standard form. Even if some are big in thousands, some are small in tens, and some are big in billions, you can standardize all of them into a normal standard value. And this is known as a z-value. For you to be able to do that, you got to know the random variable, the mean, and then the standard deviation. And then you can find that. I'm sure you've all seen this before.
Yes.
Now, once you have that standard normal, now you can use that standard normal definition to find the probability density function of a particular standardized value. So we can find the probability density function for the z value. And this is given by this formula. Of course, we also have the cumulative distribution function, which is integral of the value, with negative infinity to the actual z value in question. How can you find it? Well, so one of the ways you can find this z value is using the tables, but computer can also do it for you. There's other numerical approximations like Abramovich, Stegan series, which can also find the values for you. But we are going to use the first one, the statistical table, to do that. Before we go there, understand that there are other properties of normal distribution. One of them is moment. Okay, the moment we've already said, the moment defines the mean and the variance. So X is normally distributed with a mean of mu and a variance of sigma. The expected value is a mu, and then the variance is a sigma squared. Those are the moments. All odd central moments are said to be zero. So once you are not within the thing, you are on the flat level, you are zero. All even central moments like this are also, they are not really zero, but they are equal to that. So you can see that this is indicating sort of the variance, okay, the even central moment. Okay. The x minus the mu raised to the power scale, and that will give you this value. We can find two moment generating functions of the normal distribution, which is provided by this. You can also find a characteristic function, which is provided by this. We've said this thing before when we're looking at hypergeometric distributions. And then you can also find entropy value, which is provided by this. That will require that you know the logarithm, the natural log. So normal distribution or any normally distributed random variable has a maximum entropy among all distributions with a fixed mean and a fixed variance. You can move from normal to multinomial. A random variable x is a member of the real positive odd terms. And this is said to be having not a normal distribution, but a multinomial distribution. If the x is normally distributed, but with a multinomial value, and it has it's multinomially distributed with a mean of mu and a sigma. So this sigma will indicate all the values of the normal distribution with a multinomial higher value, which is k. So that will give you that sigma value. And its probability density function, in fact, you will not do multinomial, I'm just telling you. Okay, and this probability density function is this. It's similar to that of the normal. The only thing is that it's multinomial, so you take each particular k and extend it. The properties of the multinomial function is any linear combination component is said to be normal. The marginal distributions are normal. The conditional distributions are normal. And the variance covariance matrix must be positive definite. That variance covariance matrix is what makes it multinomial, because you have to take it for each value. So that is normal distribution. How do you know that something is normally distributed? Well, you can use graph to check. You can use histogram, and then you can superimpose the normal curve on it, and then it can address that issue. And you can also use what do you call it? A QQ plot and normal probability plot. You can use that. But then these are curves. They don't really tell you much until you have been able to formally tested. And the commonest one is using the Shapiro-Wilk test, the Anderson-Darling test, the Kolmogorov-Smirnov test, the Jacobera test. Okay, Jacobera uses more of the ketosis and the stews. All of these tests are fine. Now that we have large data set, big data analytics, some of these tests become powerful than others, especially for large data. So that is it. Normal distribution. We are going to now take a question to see how normal distribution can be applied in real life. But note that the central limit theorem states that as you increase the sample size, you are inching closer to the true value. For an independent and identically distributed random variable, that's IID, with a mean of mu and a variance of sigma squared, this normal distribution says that if you keep going up and up, okay, so this formula says that this is normally distributed with a zero mean and a single variance of standard deviation. That is for the one that has a mean of mu and a variance of sigma. That is IID. This is how it is distributed. And we're going to be using this formula in some of our work. So we're going to start by looking at an example of a situation that is normally distributed and then see how to solve it. Now continue.
Okay, so the question says factory produces precision rods whose length are roughly normally distributed due to many small random sources of variation. Historical data indicates that rod length X has a mean of 50 and variance 64, making the standard deviation to be 8. Okay, so the first question, a quality inspector accepts rods whose lengths lie between 45 and 60 mm. What fraction of produced rods will be accepted? So here I'm guessing the fraction is the percentage we are looking for. Right?
Yeah.
So if we are solving normally, then we are using the formula of Z being equal to X minus mu divided by the standard deviation. So we do that for the first part, which is the 45. Then we do for the 60. We find the percentages for the two Z's, and then we add them up. How do you want to take us to the second one? Through the second one.
Oh, okay, so for question 2.
Yeah.
Okay. So in this case, using the same formula that we just discussed, Z is equal to X minus mu over, what's that? Yeah, we already know the Z value, which is essentially 10%. So we need to go and look for the 90th percentile in the Z table. And then we already know our mean and we already know our standard deviation, which is the root of 64, in this case 8, and our mean is 50, right? So we have to just do a change of subject, make X the subject.
So what is the mean?
The mean is 50.
What do you need apart from the mean?
You need the standard deviation, but in this
Yes.
case we've been given the variance, so we find the root of it,
Which is
8.
So what do you do from there?
So we have to essentially make X the subject. So
why would you want to make X the subject? Subject of what?
Subject of the Z function. We already know the Z because we were told it's the 10%, only the 10%.
No,
so we are looking for the 90.
Question 1. I'm talking about question 1.
Oh, we have gone to question 2.
So it's question 1 I'm talking about. So summarize. What did you get for your question 1?
Okay, so for question 1, we found for 45 and for 60. So for 45, we got 0.65. And then for 60,
was
we
it positive
got,
or negative?
was negative 0.625, negative 0.625, and then on the 60 we got positive 1.25. Yeah, and so we did the we had to go and find in the Z table what lies between the two.
So you went to the Z table and then you got what?
So I haven't done
so you've not found it, but you said you got the answer, right? Even though you haven't found it.
No, I didn't have gotten the answer. I saying we had moved the question.
Did any of you get the answer? Did any of you get, or you stopped there?
No, we're yet to get to the table.
Okay, well, you had a table, didn't you?
Yes, we have it.
So now, looking on the table, what is the value?
Okay.
You have 0.625. What will you read? But you were smooth sailing. Continue.
No,
right. So 0.2625, all you do is that you take two decimals. So it becomes 0.63. You forget about the negative because normally distributed curve has got a mirror image. So the negativity doesn't matter. So it becomes 0.63. Now you come and read 0.6 here. Okay. So 0.63, you read 0.6 under 3. So this is 0.6. This is 0.6. And then the 3 is right at the top under 3.
Yeah.
Where they meet will give you 0.2357. Are you with me?
Yes, Doc.
Yes, Doc.
Okay. Now you were looking at between 45 and 60. So the best is to draw first. So when you normally draw, you draw like this, you indicate a mean, which is 50, put it in the middle. So we are looking at 45. Okay, 45 is on the left here, 60 is on the right there. So we're actually looking for this shaded region. You always draw. So we're actually looking at between 45 and 60. And the mean here corresponds to a 0, Z. A 0, Z. That is why the 45 gave us negative 0.63 because it's on the left side of the 0. So it gave us negative 0.63. And then the 60 will give us 1.2 something. What was that?
25.
So that was because it's positive. So that is the Z equivalent of the random variable X here. Now, whatever you find, so now we are looking for the area here. So the first 0.63, the one we just found, which was 0.2357. Okay. So this area is a 0.2357. Now remember, I read it going leftward. If I was looking for this area, I would have subtracted this one from what number?
0.5.
Yes, because the Z maximum value is 0.5. So you get 0.235, then you read this other area, 1.2 under 5. When you look at the table, when you are reading 1.2 under 5, what would the value?
So it's 0.3944.
44.
Good. So that is it here, 0.3944. So what do you do to these two numbers?
Look, you add.
Why?
Okay, because of how the shaded portion is. So the two will be combined.
Good. Okay, so you add the two, and whatever you get becomes the probability that you are looking for. Okay. So that is how you calculate this one. So you add the two, and then here, when you add, it becomes like the minus becomes add. So you get this one, you get that one, then you take the two, and then you add them together. That'll give you 63.01%. Who doesn't understand? I could have also asked you to find the probability that, because see, this question, you say what fraction of produced rods will be accepted? Okay, because of between that range, will be accepted between that range. But if it had been will be accepted we accept will lie above 60. I'm sure you can do that.
Yes, Doc.
Yeah. Okay, so that one, you just, whatever you find, you subtract it from 0.5. And that will give you above 60. You can even have below 45 and above 60. So you will find each one, subtract each one from 0.5 and add the combined. Does that make sense?
Yes.
Yes, Doc.
Yes, Doc.
Now, your next one you are looking at is the factory wants to set a critical K. So only the longest 10%. So how did you say you were doing about it?
Okay. So as Prof. Emily had told us, so what we were doing was that we knew that the 10% represented
Somebody is
the
echoing. I don't know why.
yeah. Jerry, can you meet and see if it helps?
Okay.
Okay. Doctor, please, it's still echoing.
Continue.
Okay. So we were going to still use the same z equals x minus mu over the standard deviation formula. But in this case, we already know that the z value represents the 10% or that the
Z value
90th
doesn't
percentile.
represent 10%. It is a probability that is 10%.
Yeah, the probability.
Remember, you have the x will help you get the z. Z will help you get the p probability. And now you already have the probability. So what do you do?
So
Well, first thing you got to do is to draw. Okay. Let's just clarify things. The first thing is to draw. The mean is still 50. And we are looking at the longest 10%. The longest 10%, is it to the right or left of the mean?
Doc, right.
Right. So you indicate a point here, and then this shaded area is that 10%, which is 0.1. But normally when we are moving, we move from the center towards there. You always move from the center going. So now that we have the 10%, you have to find this portion. Okay. What is that percentage?
0.4.
0.4. So that is what you are going to read. That is a probability you're going to read. It's not a 10%, it's a 0.4%. Because you bypass that, you normally find that. And before you subtract from 0.5, before you get a 10%. Does that make sense? Yeah. Now, so you're going to read this 0.4 on the table. So you go to your Z table, and you go and search for the number or numbers closest to 0.4. And then you find the corresponding Z value on the left, far left, and on the top right. So which number is closest to 0.4? 0.40000. Which number?
.1554.
No, which number is closest to 0.4? Which probability
Okay,
is
so Doc
closest
is between 0.3997
Now,
and
one
then
of them is closest to
0.4015.
0.4.
Yeah, that will be 1.28.
Yeah, so the one that is
That's-
closest to 0.4 is a 0.3997.
Yes.
That's all you are taking, 0.3997, because this one is far away from 0.4.
Okay.
So now that you got a 0.3997, you match its corresponding Z, which is 1.2, like Emily said, against the 0.8. So your actual value is going to be 1.28. The rest, do you understand?
Yes, Doc.
What do you
Yes,
now
Doc.
do with this 1.28? What do you now
Doc,
do
you
with
bring it back into the formula.
Substitute into the formula.
So you substitute into the formula. The formula is Z equals to X minus mu over sigma. We know that, we don't know the X now, but we know that the Z is 1.28. Are you going to make it plus or minus?
Doc is plus,
Why?
because we are dealing with the right-hand side.
Good. So you now do 1.28, then X minus the 64 The mean is 50, right?
No, 50.
50 over 8. So now you can use change of subject to find the x. Now, when you find the x, the value of the x is going to be at the junction. So if this is the 10%, the value of the x is going to be here. So it is satisfying both the 10% and the 0.4. So when you do that, you're going to get a certain answer. What answer did you get? I'm sure you all understand the principle. 60.24.
Yeah. 24.
Yes.
So that is how you exact it. This is an examinable question. Then we go to the last one. So when you round this up, you're going to get the value to be 60.24 milliliters. Okay, so the next part of the question says sample of 25 rods is taken, the sample mean length x bar is computed. What is the probability that x is 52? More than 52. How will you do this one? Now you know all the answers. So how will you do this one? It's a bit tricky, eh?
Yes, Doc, the sample mean is throwing me off.
I know. The sample mean is what is making it slightly, but you think about it, you see that it's not that difficult. It's a little thought. So first of all, when you draw, is it going to be to the right or left of the mean? It's still following from the previous one. Is it going to be to the right or left of the mean?
Doc, right.
Right. Okay. Now, which area are we looking for? Is it A, is it B, or C?
Doc, C.
C. All right, so I hope you are following.
Yes, Doc.
Okay. So we are looking at the sampling distribution. And the sampling distribution is, you know that the sampling distribution is always given by the mean and the standard deviation, isn't it?
Yes.
Good. But then, if you check, it says the sample is taken and the sample mean length is x bar, is computed. So if you compute the mean, you must also compute the variance. But we already know the variance, don't we?
Yes, Doc, 8.
Good.
Okay, sorry,
No.
64.
64.
64.
So if you want to know how x bar is distributed, then you will have to know the mean, and then you have to also know what do you call it, the sample variance. We have to know the sample variance because the sample of 25 rows was taken. So you will have to take that variance you already have and divide it by the 25 to know the sample variance. So the mean is going to be 54 or 50. But then this is a variance. The variance is 64. But then the sample variance will be that 64 divided by n. So you get 64 divided by that n that was given to you. Yeah, this is a little tricky part. What would I give you? So to give you
2.56.
2.56, that is the variance. But we are not using the variance to do our calculation. What are we using?
Using the standard deviation.
So you have to take the standard deviation of this variance. So this is 2.56. You take the square root of that.
1.6.
1.6. So now you have the mean, which is 50, and then you have the variance, which is 1.6. At this stage, you just go and find the x value. So how do you find the x value? You find the z, isn't it? So the Z formula is going to be 52 minus 50 divided by 1.6. You get a negative value. What is that? 52 by minus 50 is 2. 2 divided by 1.6.
But 1.25.
Positive or negative?
Positive.
Negative.
Hey, sorry, negative.
Why negative?
That is negative 2. Oh.
No, it's positive. It's 52 minus 50.
Okay, 52 minus 50.
So you get 1.25. What do you do with this 1.25? You go and read it. Isn't it? You know, we've already had this 1.25 earlier. You remember we had it earlier?
Yes. Yes, we had 0.3944.
Exactly. But now, looking at what this person is asking, what do?
So you subtract it from 0.5.
Exactly. So your final answer is going to be 0.5 minus 3.3944.
Yes.
What is your answer? Jerry and the others, they are closed.
Oh, we are here.
You are not here. Otherwise, I will hear your voice. So what do you get? The final answer is going to be 10.56%.
Okay.
10.56. But do you get it? So what this means that the chances of you picking a sample of 25 and actually obtaining 52 or more millimeters, the chances are very slim. It's approximately 10.56%. That's it. Any question? You have a test, too. That's why I want you to be ready. You get it before you start the test. Any question before we start the test? No question. Question or no question? You are cool. Okay. Now we're going to look at a certain proof before we come with a test. Oh, that one we are working together. The proof. So there's something we call affine transformation. Affine transformation. What do you understand by affine transformation? What do you understand by affine transformation? Emily?
Got no idea.
You heard about the word affinity?
Yes.
In geometry. I mean, you are a mathematician. You know, there's a difference between straight line and parallel lines and ratios. You know a straight line?
Yes, Doc.
And you know a parallel line. So anytime you can shift something to something in a direct opposition, just like the normal distribution, that is alpha. You can scale a number. Okay, you can scale a number which is a numerator, say 10, and the denominator say 2, and scale them by 10% or 100%. The 10 moves to 20, the 2 moves. That's an affine transformation. You can rotate an object around a point. That is an affine transformation. Or something we used to do called reflection in secondary school. You remember reflection, the angle of
Yes.
reflection? Yes.
Yes.
So all of these are affine transformations. It's a vector, it's a matrix, where rotating, scaling something, you actually get back its translation vector. Okay, so because the normal distribution exhibits, the normal distribution curve exhibits that affine transformation, we are going to check something. If we say that X is normally distributed with a mean of mu and a variance of sigma, how do you prove that? How do you prove that for constant value A, which is not 0, and B, the random variable that you see here, no longer X, but this random variable Y is actually that constant multiplying the X plus beta? Now, when you look at this very thing, it reminds you of what? Look at it carefully. What is that?
Equation of a straight line.
So in other words, prove that this equation of a straight line is normally distributed. If the X, which is here, is normally distributed with the mean of that and the standard deviation of that. And then after you prove that, find the mean and the variance. Let's see how you can do that. So first thing is that we use a transformation method on the probability density function, because the probability density function exhibits a transformation method. Okay, so we're going to let Y be AX plus B, and we can make X the subject of that formula. I was going to say you should make it, but I've done it here. When you make X the subject of that formula, what do you get? You divide both sides by, so you move this one to the lesser. That's why you have Y minus B all over A. Do you get it?
Yes.
The probability density function for X is going to be this. We know this already, that the general PDF for any random variable is that. Okay, we set the probability density function for X, but we didn't set the probability density function for Y. So how do you get the probability density function for Y? Instead of X, we are going to put in what? Y.
Why?
Because so wherever we see X, we are going to substitute that with Y. So the probability density function for Y, by changing the variables, is going to be this. So watch this. F of X is going to be Y minus B. Now, why Y minus B? Because here, we already know that this X is Y minus B all over A. Okay, so that's what you have here. So that's an X, Y minus B all over A. And then you see that, where is that? Then you have 1 over the absolute value of A. Now, why do we have 1 over the absolute value of A? One over the absolute value of A. Because when you look here, it is this whole function. Remember, it is Y equals to AX plus B. Okay, and X has been substituted here into this function. Do you guys get me? This X has been substituted here. So you are going to have Y equals to A, and then Y minus B all over A. Okay, and then plus B. So whenever you have X here, you put in this value. But whenever you have Y, you put in the whole of this value. So when you go back here, you have Y minus B, which is the X defined. But we are actually looking for the probability density function for Y. And Y itself is is a whole function. So when you look at this, watch that. When you take the exponent of whatever is in the bracket, x, again, here, you are going to substitute that by this whole of this x. And then you have the mu, the squared. Okay, so it's the whole of that y minus b all over a minus the mu. Actually, there should be a bracket here, minus the mu before you square it. Okay, because it's an x minus a mu. Okay, so this whole thing is an x minus a mu, then you square it. All divided by 2 pi squared. Let me just go back in. Okay, so you take the exponent of this, you substitute all of this formula. Now, if you look at the second one, the first one, you have the square root of 2 pi sigma. That square root of 2 pi sigma is exactly represented here. But remember that the a, the y multiplying the 1 over the a is because when you substitute for the y, there is a b attached to it, but we don't need that b because that b is a constant. It's not having a multiplication like the a is having a multiplication. And so you now break it down and you get this function. Then what you do here, you rearrange the exponent. When you rearrange the exponent, you get this. Let me just delete this one first. When you rearrange the exponent, you get this. Okay. Remember that the a is squared. It comes down. Okay, because it's already a denominator, so you multiply this one. The numerator is left with y minus b, but they are both squared. And then this a, this mu is also squared. And so you're going to get all of them squared. I'm thinking I use what do you call it? The minus. The minus has to be applied to this. So you square them and you're going to get 1 minus b minus a mu all squared. That minus is applied because of this minus above here. And then the a, which is also squared, comes down, and that's why you see 2 outside. Okay, a squared minus, when you take the exponent, because when you take the exponent of the number, it's still within that 2. So when you rearrange, you get this. Now, at this stage, you can now say that the f of y, which is finding the probability density function for the x, but this time for the y, is going to be this function 1 over here, 1 over the same thing here, 1 over 2 pi, okay, the absolute value of a sigma, the exponent of whatever you have here, all raised to the power 2. And that is the probability density function. Suppose that we are doing it for the equation of a line instead of for the equation of, so this becomes a probability density function of x, but this time the mean will change. Okay, so you see that this becomes a probability density function, but the mean will change because now the mean has become a mu plus, because normally it would have become mu, but this time it becomes a mu plus b. And then the variance is going to be the item in the bracket here, which is this. So we can say that y is, instead of x, we say that y is normally distributed with a mean of this, okay, au, this comma doesn't come, a mu plus b, and then you have a variance of a squared sigma squared. Go through it and then familiarize yourself with that. Okay. So this is how you are able to prove this question. This is how you're able to prove that this is normally distributed. And if it's normally distributed, this is a mean and this is a variance. Well, the mean and the variance are what we just peeled off from here. If you go to the original one, look at the original one. The variance is what is multiplying this. The variance is always what is multiplying the 2. And the mean is what is up here. Okay. But with this y, with this final derivation, the variance becomes what is multiplying the 2. And then the mean is no longer what we had, but it becomes what is up here. Okay, that's it. Now, I wanted to solve this within a certain time frame. I'm going to give you a time frame to solve. You can have this as a test, which will conclude the test you have, which will now help you. Well, the thing is that you can't even have it as anything except as a test. It's only as a test. Okay. We're going to do this as a test, and we're going to work it on a paper, and then you take a picture and send me the paper. It has some 4 questions. It's a very, very simple question. Very, very simple. Just like the first.
Doc, is this the same one? It seems the first one was different.
And I know it looks like it's the same one, eh?
No, Doc, are there 2
it's the
different
same one.
questions? Like,
It's the same one.
can you please go back 1 step? I think there's a question before this. Okay.
No, you're right. In fact, just hold on a second. Let me see. So you have that. You have this constant. The actual weight of each bag is approximately normally distributed. Quality assessment records show that the weight have a variance of 49 grams. But of course, the mean is already given. So you have this question. The quality control department only approves coffee bags that weigh between this and that. What proportion of the bags meet that requirement? Management want to create a Royal Reserve Edition using only the top 8% heaviest bags. What is the minimum weight needed for a bag to qualify? The quality supervisor selects a random sample of 36 coffee bags, computes the average weight. What is the probability that this sample exceeds 203 grams? If 2 bags are selected randomly from the, what is the probability that both fall within the acceptable weight range identified in question 1? So do you want to do it now or later?
Doc now.
Good.
Oh,
so
guys.
You have 30 minutes. Let me set the time.
Doc, please, when you were explaining the proof,
Well,
did
let
it
me
record?
send you. Sorry?
When you were explaining the proof, did it record?
I think so.
Because if it didn't record, I'm dead. I'll need to go over.
It's all here. Proof is all here. Okay. I was talking about the affine transformation. We did. I think it did. It did have everything because I turned it up when I was going to do the test. That was when I paused it.
No, okay.
Yeah. They had everything. Okay, so let me set your stopwatch. 30 minutes. You go for it. Now, let me send you the question. Say a hello on the page for me. I just want to send you the question so that at least I don't have to be coming to toggle between these 2. Well, I think I can let you take note of this first part, and then I just let the thing stay on the second part, isn't it?
Yes.
So the information you need here is what? Sorry?
Oh, so you have
This
to
is
pause the timer.
pause the timer.
Oh, shut up, shut up, shut up. What information do you need here? Only 2 information. What are they?
Not the mean and the variance.
Do you have it?
Yes.
Good. So if you have it, I'll let it all stay here. Start. Let me restart and quickly look at the situation. If you got it, you know. Okay, if you didn't get it, you know. Are you guys there? I mean, you know that normally when we work, I like to do the answers quickly. And then
Yes, Doc.
Yeah, so that is it. So let's look at the first part. The question says, The proportion of the bags that meet the requirement. The proportion of the bags that meet the requirement. Some of you, this time I can't even see the writer. Okay, so let me look at yours first. You have 0.88, 88%. Is that it?
Yes, yes, Doc.
This one too had 87.97%, also 88%. That is Albert, either.
Yes, Doc, I'm here.
And Jerry, you had. Yes, it's very, very complex. I can't even understand. Okay, 88%. Okay, so that one is 5 minutes.
Doc, please, you said 5 marks.
Yes.
Okay, so 555.
The next one, when you work it out, you should get approximately 209.8 something grams. Emily, you had that. Albert, you had that. Jerry, you also had that. So that is 5.
Okay.
The third one is about the sampling distribution, which should be approximately 51%. Jerry? No, you didn't get that.
I didn't convert it into percentage, but when I convert it, it's the same thing.
Oh, yeah, 0, it's actually 0.51%, actually. Yeah, you got that. And then, Emily, you had that. Then Albert. Albert, that one is not clear. Did you get that?
No, I didn't subtract, so I didn't finish the process.
2.57.
Yeah.
Now from there, you didn't get the other. So that is 3.
Yeah.
How many got that?
Yes, Doc.
And then the last one, Albert had 0.
Okay, you can try.
Jerry, you had it all correct, 74, 77. And then Emily, you had it all correct, 77. Okay. So, Emily, you have the total.
Yes, Doc. It's 2013.
Okay, yes. Now, Jerry, your auditing came late. I'm deducting 2 marks for being late. So that next time you are not late.
Please, I was not late.
I knew.
I said it.
I was very specific and I knew you were going to be late. And then you became late. I thought you would surprise me. And then you're this late. So I have the time you sent here. And then when I juxtaposed that time, you were 1 minute, 6 seconds late.
Oh, no.
What's over? I told you. You said that. You even said you were even frustrated at some point. You remember? Because you were trying to do something and it wasn't coming. Okay. So
because
this is exactly the work you've all done. Now I have a homework for you to look at. Okay. This is it. It's a proof that I want to. If X is normally distributed with a mu and a variance, prove that for any constant, this is the case. Oh, I think we've done this. Yeah, we've done this. Is the second one. If X1 is normally distributed with the following, and X2 is also normally distributed with the following, they are independent. Okay, then X1 and X2 is normal. And if so, prove that and find the mean and the variance. So it's a question 2 that I want to try your hands on it. Try your hands on it, you never know. Try your hands on it.
Yes, Prof.
So that is it for now. I wish you all the very best. If you have a question, you can ask now.